Hello, welcome to Undergraduate Lecture 1 for a modeling series. The topic of today's lecture is Introduction to Modeling. My name is Luke, and I'm a PhD student at Cornell University. The lecture today will go over several topics, which include the concept of modeling, primary growth model, secondary growth model, model evaluation, Monte Carlo simulation, as well as quantitative microbial risk assessment. First, let's talk about the concept of modeling. Upon completion of this section, you will be able to explain the definition of a model and then explain the purpose of applying modeling approach. So what exactly is a model? By definition, model is a simplified representation of a system in which a system is a process of interest. A system can be very small or very large depending on its complexity. For example, here we have a list of systems: a bag of lettuce, a produce farm with multiple fields, a food processing facility, or an entire supply chain. As you can see, as the scale goes up, the complexity increases. However, depending on our research question, we can narrow down the system to its essential components. For example, in terms of a bag of lettuce, if you are interested to know what will be the spoiled time of this bag of lettuce, we can ignore many components of this bag of lettuce, including pH, oxidation rate, and other factors, and leave only the most important component, which are what are the spoilage microorganisms in this bag of lettuce, as well as its storage time and temperature. This simplification is very usual when we are studying the system. So why do we want to model? The essential of the model is to solve real-world problems. There are a lot of real-world problems. For example, we can define the problem more accurately, as I mentioned earlier. And again, with this model, we can organize our knowledge by selecting most relevant information about this physical system. Another way of using the model is to better understand the available data. A lot of experimental data can be exploited to make a model for more usage. We can also test our knowledge by using a model. By generating a hypothesis, we can test this hypothesis with the model we develop. We can also determine dominant factors that generate observed patterns and phenomena using our model. This can be done through sensitivity analysis. By modifying certain model parameters to different levels and observe their effect on the model outcome, we can evaluate their importance. The most common way of using a model is to predict. The prediction allows us to act beforehand when we know the prediction results. Another very important way to use a model is to support decision-making. This is fairly widely used in government, as model can help us make decisions whether or not to perform a certain action. Now let's talk about a very important model type, and it's also a very essential one to begin with. This is primary growth model. Upon completion of this section, you will be able to explain the purpose of using a primary growth model and develop a primary growth model with an online app where I demonstrate. So what is a primary growth model? We define a primary growth model that is a model that can describe microbial processes, for example, growth, inactivation, or survival, as a function of time. So there are two steps of this model development stage. The first is to estimate parameters for these microbial processes. For example, if the microbial process is the growth, we may be interested in the growth rate. And then, with all the parameters estimated, we can simulate this microbial process with our estimated parameters. We'll showcase how we can do that in the following examples. Now, let's put it into a context relevant to produce safety. Suppose our goal our research goal is to understand the growth of Pseudomonas on lettuce over time. This question can have practical implications. For example, if you are hired by a food company and your manager wants you to test out how long your product can last in refrigerated temperature until it is spoiled, you may want to conduct some experimental data to estimate an expiration date for your products. This is a very natural thing to do to begin with. So how do we proceed with that? The experimental approach can be fairly simple. To get a more representative understanding of microbial load, we probably will mix several bags of lettuce and store at 40 degrees C over 3 weeks, which is a usual refrigeration temperature. For every 3 days, we may take a sample, say a few leaves, to perform microbiological testing. In the testing, we want to enumerate Pseudomonas species from the sample and record the count. With that data, we can plot it in Excel, and then we can clearly see the microbial growth over time. To know when our product will be spoiled, we might already know a spoilage threshold beforehand. So if we know that, we can find a horizontal line in this plot and find out the corresponding time when the microbial loads exceed the spoilage threshold. In our case, this number is determined at 15 days. So we can simply say that this product's shelf life will be 15 days. However, this is not always the case, because we have to assume that every bag of lettuce starts with initial bacterial count at 3 log per gram, which is unlikely. So do we have to perform experiments for every bag of lettuce? Probably not, because this is not a realistic way to do it. So a more appropriate way to approach this is through modeling. This is where we want to model the microbial growth so that we can understand its growth pattern regardless of its initial bacterial load. Here, I want to introduce you to a very useful web app called MicroRisk Lab, and you can find its link in this photo here. This is developed by a group of researchers in China, and it is currently available free online. Following this, I will showcase you how we can use this online app to perform model estimation. So the first step we want to do is to estimate our parameters. In the plot we generated, it is a very ideal growth pattern. We can see from this plot, straight away we can define a certain distinctive features. For example, if you have taken basic microbiology, you will know the growth pattern can be divided into lag phase, exponential growth phase, and the stationary phase. So from this plot, we can see that the lag time is roughly 3 days. And the initial concentration, as we defined earlier, is 3 log per gram. The maximum concentration, which is defined as the environmental capacity of these microorganisms in certain food matrix, here we can see this value is 8 log per gram. To know the maximum growth rate, we simply find the slope of this plot and use that as the maximum growth rate. So we have all these values, but in real life, the plot may not be as ideal as this. So we want to find different ways to estimate our parameters. This is where we use this online app. In this online app, you will find different tabs on the left-hand side. To estimate our model parameters, we select parameter estimation. Since we're using primary growth model, we select primary models and then select growth. There are different model choices here, but for the demonstration purposes, here we'll select GUMPers first. In the next module, we'll talk about different ways we can evaluate model and select model type. As you can see here, there is a sheet we can import our data. So here we imported our data into this data sheet. We know what time it is and its corresponding counts. Once we imported data, we click Fit. The model will run very quickly. Here I want to point it out our model estimation results in this red box. As we can see that it automatically approximated different parameters that we defined earlier, which are mu max, which is the maximum growth rate, lag time, initial count, and maximum population density. Now we just need to record this number for later use. As we can see that using the GUMPers model, this is the fitted curve for our primary growth model. To use this model for simulation, we'll be using this fitted curve later. So the next step is model simulation. This is where we use a model. For example, if we know a certain initial bacterial load and the maximum growth rate as well as lag phase, we can use this model to simulate the bacterial concentration at any given time. To use this model simulation, again, we go to this website and select model selection. In static models tab, we select growth because we're dealing with a growth model. There are two types of model. One is deterministic, which will give you a fixed value. In our case, it's a fixed microbial concentration. There are other model types that can give you stochastic results. We will not be teaching this for this class, but this will very likely be show up in following lectures. So because we use GUMPers model for the parameter estimation, here we again select GUMPers model. And after click simulation, we will be shown different model parameters to input. So the model parameters are from the values we collected from the parameter estimation results. We can see here we input maximum population density at 8.8, lag at 3.78, mu max is 0.91. And the condition can vary depending on our situation. Suppose in your company, this time you got a batch of lettuce that has less initial bacterial counts. Suppose this value is 1. Now we can simply estimate its shelf life or its spoiled time by using 1 as initial counts. So here we input 1. And just for safety, let's put 35 days as time to see how the microbial counts progress over time. Now we click simulation. The model will run fairly quickly. We can see here, this is a predicted curve for microbial concentration over time. And again, as we already know earlier, if the spoilage threshold is 7 log per gram, then we can roughly see that our shelf life is at 20 days. This is 5-day improvement from our earlier example, which has 3 log CFU per gram as its initial bacterial count. Of course, you can further customize this model depending on your initial count. For more, this app is very convenient to use, but It is actually a Shiny app that is based on a statistical software called R, and everything from this interface is hard-coded in this software. If you want to use more advanced and customizable analysis, you can learn how to use R to do that. We will not teach that in this course, but feel free to explore on our own. Now, we only need to sample once at the beginning to have the initial concentration, and with this model, we can predict the bacterial count at any storage time using this N0 initial concentration. This will save us a lot of time on the experiments. Next topic of today's presentation is secondary growth model. Upon completion of this section, you will be able to explain the purpose of using secondary growth model, develop a secondary growth model with an online app, and identify different advanced methods for developing a secondary growth model. You might wonder, we already have the primary growth model. What exactly is a secondary growth model? So the secondary growth model describes premise of microbial processes as a function of different factors such as pH, temperature, water activity, and the concentration of preservatives. For example, the parameters of microbial processes used in our primary growth model are lag phase and maximum growth rate. So our maximum growth rate will be dependent on various factors. One of them is temperature. This is very relevant to our practical example because we cannot guarantee our lactose will always be stored at required temperature. For example, what if the transportation is in summer and the cooling system of the truck is not reliable? What if the consumer left the lettuce in a car for an hour because he or she is driving from a supermarket to home for a long way? What if there's a failure in a refrigeration unit at a retail store? Can we predict the shelf life more reliably if that disaster case happens? These are the practical reasons why we need secondary growth model. As I mentioned earlier, microorganisms have their own optimal growth conditions in terms of temperature and pH. Once the temperature changes, the maximum growth rate and lag phase will vary. Naturally, a microorganism will grow faster at higher temperature if this temperature is below its optimum temperature. So with that knowledge, how do we predict the microbial loads more accurately if our temperature shifts a lot? Again, we can seek experimental approach. I will illustrate how we do that. So for experimental approach, we simply repeat the experiment we previously described for multiple times at different temperatures. Previously, we did it at 40 degrees C. Now we are going to repeat it on the different storage temperatures, which are 7, 13, or even more. Again, with that experimental results, we plotted them in this plot. We can see that at 13 degrees C, our shelf life shortened substantially, resulting in only approximately 6 days. And with 7 degrees C, our shelf life is shortened to about 9 or 8 days. However, to know the shelf life at different temperatures, we have to conduct more experiments to find out. What if the lactose is stored at 10 degrees C, a temperature we did not collect the experiment data? We can do more experiments, or we can seek modeling approach to predict or extrapolate the parameter at an unknown condition. Again, Using a secondary model, we have two steps. The first step is parameter estimation. Let's go back to our micro risk lab and select secondary growth model. Because we're here for simplification purposes, we're only interested in the temperature as the primary factor that impact the growth. So we select growth temperature. And the parameter we care about is the specific growth rate. Here, there are different types of secondary growth model. For simplicity, I will select subordinal square root model here. We can see that here is a data input sheet. We have to input the we have to input the maximum growth rate at different temperatures. Assume we repeat the same process as showcased earlier for maximum growth rate at different temperatures. We have the 3 points here, 3 data points here. We click fit and the model will run. As you can see here, with this information, we can predict the maximum growth rate at different temperatures. Looking at this fitted curve, we can extrapolate the maximum growth rate at other temperatures that we did not collect experimental data on. For example, if we are interested to know what the maximum growth rate is at 10 degrees C, we find the point on this fitted curve, and this pointed us to the value 1.74. And we can use this as our mu max in our model simulation section. With model simulation, we go back to this web app, select static model, just like we did for the primary growth model, because we're essentially using a primary growth model, but with the different model parameters. Everything else is the same. For example, the maximum population density will not change by the temperature. However, the lag phase and the mu max will change depending on the temperature. Here, although I didn't show the process, I also calculated the lag phase at 10 degrees C, just like how I calculated the mu max at 10 degrees C. So I input these two values. In condition, again, we select 1 as our scenario, select 35 days as our time, and click model simulation. Again, the model will run. We can see that the progression of microbial load over time. With higher temperature, we're seeing the higher microbial growth over time. So here we can see that at the intersect of bacterial count and the time, we see that the shelf life is shortened to about 12 days when the temperature is increased to 10 degrees C from 4 degrees C. So with that combination of primary growth model and secondary growth model, we can basically predict the growth for growth of microbial under different temperatures and different initial concentration. In reality, however, the secondary growth model can be more complicated because the example we showed there, the temperature and the growth rate are linearly correlated. However, there are examples that the temperature are beyond the linear range. For example, if we want to know the growth rates over 30 degrees C, which is the optimal temperature, the growth rate will actually drop. So our linear prediction will not be reliable. Also, temperature is not the only factor that impacts the growth rate. What if we have more factors, such as pH, that will limit the maximum growth? In that case, we have to do more adjustment and even consider that there are synergistic effect on the growth rate. Moreover, we do not only want to address the growth rate, we probably will also adjust the lag time or other primary growth factors. So here I just want to showcase one of the different secondary growth models that can adjust parameters in primary growth model to specific conditions. This is called gamma concept, and it's fairly easy to understand. Basically, the growth rate at the actual condition will be compared to the growth rate of optimum growth conditions for a single factor. And we can find this ratio for different factors and combine them together to calculate a combined effect of different factors. Basically, if the growth condition is more deviant from the ideal condition, the growth rate will be lower. This gamma term can be calculated like this, and we can calculate the gamma term for different factors such as temperature, water activity, and pH, and then multiply them together with the growth rate at optimum condition. So here we can obtain the growth rate at the actual condition. This is just one example of secondary growth models. And again, in the next section, we'll show how you can evaluate different secondary growth models and how you can select which one to use. So back to our question, how do we modify our primary growth model so it is still reliable under various conditions? The answer is to complement it with a secondary growth model. Now let's move on to model evaluation. Upon completion of this section, you will be able to explain the purpose of model evaluation, evaluate the model performance, select the best fitting model with an online app. In the previous two examples, I simplified things a little bit by selecting one type of model for you, but in reality, there are multiple types of primary model as well as multiple types of secondary model, and you will have to choose which one to use by yourself. But how do we do that? One type of question typically associated with this are, which type of model should we choose? How can we measure model performance? So let's return to our example for our primary growth model. Suppose we already collected the growth data. It's 4 degrees C. What is the next step? In my example showed earlier, I only used the Gompertz model, but in reality, we would try out different model types and see which one fits better. So for the primary growth model, there are different models previously developed by other scientists. For example, Buchanan, Berani, and Gompertz. Among these models, we will try them one by one and select the one with the lowest error or lowest information criteria. By definition, this is a process of model evaluation, which is the measurement of model performance by comparing the predicted values with observed values. The two criteria we typically use are error and information criteria. The error is simply the deviation of predicted value from observed value. For example, when we use a primary growth model to predict the microbial concentration at a certain time, we can compare it with our actual experimental data and see how far away it is from actual experimental data. If the deviation is small, we can see our model is more accurate. For information criteria, it is relatively more complicated, and it's a statistical term. But simply put, it is a balance between error and simplicity. So less error is not always the best. We have to take into consideration the model simplicity, which can be defined as the number of parameters. A rule of thumb is that less error or less information criteria, the better the model. So again, we can perform the model evaluation by testing out different model parameters in our micro risk lab. We basically select different models and feed the same data for multiple times. And with this, we can see that here, the first three are the error term, and last three are the information criteria. We can record this data or this model performance and then compare them later. Here, I record the model performance for 3 types of models. Here we can see that by comparing them, Buchanan model did the best job because the error is essentially zero and the information criterion is very, very low. This is the ideal situation because Buchanan model is basically a three-phase linear model. That's why we see zero error. But in reality, because of the complexity of microbiology, you won't be able to see the error that low. But in our case, we should stick to the Buchanan model if we want to predict the microbial count. Now let's talk about a different concept that's very important to modeling microbial growth. That is Monte Carlo simulation. Upon completion of this section, you will be able to explain different statistical distribution. You will be able to describe the process of fitting real-world data to a statistical distribution and explain Monte Carlo simulation. So far, we're dealing with predicting concentration over storage from one given initial concentration. How do we deal with concentration from hundreds of thousands of products in the real world? As a company, you are probably receiving hundreds of thousands of products every day, and we cannot guarantee their initial bacterial load are the same. So we have to find a way to represent their initial bacterial load as a whole, as a population. How do we do that? Well, we can perform sampling from lots. If you have taken statistics class, it is common to use samples to represent population. Here, we can collect the Pseudomonas species concentration from 100 bags of lettuce out of 100,000 bags. We record the concentration of this of Pseudomonas species on this bag of lettuce and make a box plot from our concentration data. It may look like this. And now we want to find a way to represent this data in a statistical term or statistical distribution. There are different statistical distributions and they all have different shapes. Basically, statistical distribution can describe a population in a few parameters. Here are the three most commonly used statistical distributions: normal distribution, uniform distribution, and Poisson distribution. Here we can see that normal distribution and uniform distribution both have two parameters, where Poisson distribution has only one parameter. So how can we fit our data into a certain distribution? Here is a box plot, and we can simply use a function R that can help us fit our data into a normal distribution with mean of 2.98 and a standard deviation of 1.57. So with these two values, we can describe the whole distribution, which are 100,000 bags of lettuce microbial concentration. Then we can perform Monte Carlo simulation. We use this normal distribution to represent the true population, which is Pseudomonas species concentration of 100,000 bags. So if we want to apply the growth model to all of them, we perform rainbow sampling. Basically, we select one concentration at each time and apply the primary growth model and calculate the final concentration. We repeat this process for 100,000 times. Thus, we can obtain 100,000 concentrations of Pseudomonas at the end. With that, we can know, for example, at day 20, what is our concentration population look like for the whole batch of lettuce. Now let's talk about the last concept, quantitative microbial risk assessment. Upon completion of this section, you will be able to explain the purpose of developing a quantitative microbial risk assessment. Because QMRA, which is short for quantitative microbial risk assessment, is a fairly complex concept and difficult to model, we will be spending more time on this in our next lecture. But let's talk about why this is important to understand. In our previous examples, we're using a static temperature for our storage. However, in real life, between the production and consumption, our lattice is not stored at the constant temperature. The process in between can be very complex than just one growth model. In this case, we may need more than one growth model, and we need more time and temperature conditions at different stages of supply chain. And this can get more complex than that, because microbial can grow, die off, or be in a stationary phase. So growth model may not always be the way to go. We may need an activation model. Furthermore, products can be merged or partitioned. So in this way, the concentration can increase or decrease depending on our unit. Also, temperature can fluctuate. For example, in summer, we have higher temperature, while in the winter, we have lower temperature. Also, depending on the stages of supply chain, we can have different temperature profile. For example, as retail storage, we can expect the temperature to be more constant because we have a good refrigeration system. However, during consumer storage, the temperature may vary a little bit more because each consumer are using different refrigeration system, and depending on how consumers care about their produce, they can be store them at different temperatures. Also, our prediction outcome can vary a lot. Here, we only care about the spoilage time for our products, but this can vary different. The most common way to use quantitative microbial risk assessment is to model the final risk, which is the likelihood of getting foodborne infection. For the company, they may also care about other enterprise risk, for example, the number of recalls, because this is directly associated with their economic status. For government, they may care about other prediction outcome, which can be the number of foodborne units and consumers, because they want to model this outcome for an entire population rather than for individual. With that in mind, we can already see how complex our quantitative risk assessment is and the knowledge we need to complete this analysis. So to understand the risk assessment model, we can simplify them into a process diagram of products from production to consumption. And then, as I mentioned earlier, we want to finalize the details in each stages. For example, the time and temperature distribution, the growth or die-off or stationary pattern at each stages. And we can calculate the change of pathogen or spoilage microorganism concentration in each step. Accumulatively, we can predict the final concentration in a population of produced product or in a single serving of produced products. We'll talk more details about this in the next module. With that, I would like to thank you for listening through this lecture, and I hope you learned something. And if you want more details or if you have any questions, please feel free to contact me by my email, cq87.cornell.edu. We'll see you in next lecture.